My name is Dave Sontag from CTOS Technology, and I have with me here Martin Timms from Microzest UK. Say hi, Martin.
Hello.
All right. And Martin and I have our video turned off to spare some bandwidth, and we will mute as much as possible because we want to let Jeff Smigelski, who is the CEO and founder of sNoise Research Laboratory, describe his fractional scaling digital filter technology. Martin is heading up the engineering effort to develop a software development kit and hardware instantiation of these algorithms, which we think have some great promise in audio, but also in the biomedical realm for EEG, ultrasound, and some other things. And we're hoping to get some partners excited to work with us on bringing this technology into many industries. All right, Jeff, with that, over to you.
I will start out by just introducing the filters in general. The filters are based on fractional calculus in terms of what's called a fractional scaling exponent. And if you look at the time domain, any time series or signal in transfer it into the complex frequency domain using the fast Fourier transform, and then look at the spectrum and fit that with a linear least squares fit slope, you will find a scaling exponent, and that scaling exponent is representative of the active integration or differentiation of a signal. So, for example, if the scaling exponent is 2, that's an integration being performed on the signal. If the scaling exponent is -2, that's a differentiation being performed on the signal. And if it's described in terms of a Laplace equation, the Laplace equation for a capacitor, 1 over S, where S is j omega, or the complex frequency. The modified form of that would be 1 over S to the beta over 2, where the beta is the scaling exponent. And so this is written, beta is defined in terms of the power spectrum, not the magnitude. So then when you, that's why there's a division by 2. So when you calculate the magnitude from that, and then the phase, you get the magnitude is 1 over omega to the beta over 2, and then also the phase is minus beta times pi over 4 for positive frequencies. And so that dictates the slope that you receive. So from that, you can write the Laplace equations in terms of the fractional scaling exponent, and you can develop a set of equations that become a filter bank from which you can draw from to synthesize or reproduce any sort of filter you want with any slope and change in gain value, clearly defined where you want without introducing the artifacts of traditional filtering equations that use coefficients and the traditional methods. So, for example, we can have a high frequency amplifier, fortunately a lead filter, where when you solve this with a scaling exponent, the K value or the gain value is where the spectrum will change at 3 decibels. So there'll be 3 decibel amplification of magnitude occurs at the gain value, K. And phase, that's also where there's a plus 45 degree phase change that occurs at that frequency as well. And then you also have a low-pass filter that it's pretty much the inverse of the high-frequency amplifier, where at the gain value it bends down at -3 decibels. And this is fairly standard for digital signal processing, but the difference is including the scaling exponent. Also, with a resonance filter, that is defined by where you want the resonance peak to occur, and that's the central term within this equation that will define that. So with these examples, for example, if I wanted to build a bandpass filter, I can group together 4 of those equations in terms of a building block. So the value K is a multiplier. It just shifts the spectrum up or down by a specific amount. And then I have a high frequency amplifier, then a low pass filter, another low pass filter, and then another high frequency amplifier. And what that does is that when you solve it for magnitude, you get an equation that has the same order of the, in terms of the order of the equations from the filter bank that I just had showed. In phase, you also have the phase information that you can leave in or out of the final equation when you're solving it. But the end result is that if you look at the filter itself, this is the bandpass scaling filter in terms of the decibel magnitude, and then you have frequency on the x-axis. So the K value shifts the filter down by a certain amount, and then you have the high frequency amplifier coming in basically at what would have been 0 dB, but since K has shifted it down, now it's at minus, just about minus 50 almost. And the high frequency amplifier comes in, and at the K value, since the scaling exponent is set to a high amount, so you could set it to 100 in terms of the beta value. That's causing the slope to shoot up in terms of at the frequency of K, and then delayed a little bit is the low pass filter that comes in, also set to 100, but K is at a slightly higher frequency, so then that actually cancels out the high frequency amplifier, flattens out the pass band. Then you have another low pass filter that comes in, bends down the spectrum at K3, and then you have another high frequency amplifier that's going to cancel that out at K4 and present to you this bandpass filter that you see here, where you can define the stop bands to be the same on each side. There is some equations that you can use where you can just define the pass band in terms of K2 and K3 and how big you want the width of the transition band to be, so that it will auto-calculate the values for K1 and K4 so that, one, it's even on both sides. Now, additionally to this, what we can do is we can take what's called an altitude exponent, and we can take that equation that I showed before, that was in polar notation, and once we solve that for rectangular notation, we can actually wrap that equation with another exponent, and that becomes what I call the altitude exponent. And what that essentially would be as if you had almost a dial, where once you have the general equation set up, any region that's flat will just change according to that altitude exponent, which is equivalent then to the decibel change that you want. And any region that's slope is actually going to modify the slope according to the exponent as well. So if you have a bandpass filter with that altitude exponent, what happens is that the level of attenuation that you get in the stop band portion will be exactly defined by the whatever the altitude exponent is set to. So that if you wanted, for example, 22.5 decibel reduction, you could just set the exponent to 22.5, and you will see a bandpass filter that has a 22.5 decibel reduction. So for the process basically is you have the magnitude and phase information in terms of a filter component library that contains the fractional scaling exponent on them. You solve those for whatever type of filter that you want. That generates a complex number array in rectangular notation. Then you can add in the altitude exponent, which would wrap the complex number array, so that essentially what it'll allow you to do is to make every frequency its own bin, so that you could actually take a complex number array that is initially set to -1 dB, and once you wrap that with the altitude exponent, then that complex number array will become a new array that whatever you set that altitude exponent to will be the decibel level of amplification or attenuation at that specific frequency. So then just in general, how you perform a convolution in the frequency domain, you take a time series input, multiply it out, or convert it to the complex frequency domain through an FFT, and then you just take the complex number rectangular notation of the input, multiply it out by the complex number notation of the filter that has the altitude exponent that's solved from the original fractional scaling digital filters. And then that produces a new output that is scaled and shifted according to however you defined it in your filter component library. And then when you inverse Fourier transform that will produce a new time series as output that will give you exactly what you want. So as an example, if we look at this in MATLAB. So right here we have a pure noise. This is a beta value of 0. This is just a white noise generated through a random number generator. And we can, because I have defined this spectrum in terms of the altitude exponent, if I just draw a filter on the screen, no matter what filter that I draw, so we can draw a really complex filter, it can be as complex as we want. And any of the lines that you see that form, if I draw too fast, are just an artifact of the drawing in MATLAB, not the filters. So we'll just draw a filter, and whatever filter that we want to draw. So if we filter that series, it instantly just shapes the time series to be exactly the filter that I just drew, and shifts and everything. And we can listen to that time series. Also, if we inverse that time series, we get back to the original filter that we had. So we can also, with this, we could create a series with multiple harmonics. So if we were synthesizing music or some sort of notes of a musical instrument, or trying to synthesize speech, you could do that. So if I was going to filter this, you see that now I've created a new time series, and you can see that the filter exactly lines up with the shifted values of the magnitude spectrum that you see. And you can completely recover the original data set. This is also a way to generate pure noises in terms of, like this is a Brownian motion time series, and if I wanted to, I can actually, so if I wanted to kind of recreate the original white noise that created this Brownian motion. So Brownian motion is made by integrating a white noise signal, so you can do a running sum or cumulative summation of the white noise signal. That will get you to a scaling exponent of 1.8. If you integrate it instead in the frequency domain, just by multiplying it out by the 1 over s to the beta over 2 fractional scaling digital filter, then it will be exactly 2. So you see that the scaling exponent of this spectrum is exactly 2.000. And if I filter this now, you'll see that now I get back to a white noise signal that I originally had. And inverse filtering that, we get back to the original Brownian motion. If we wanted to actually integrate the signal again, that's going to be 2 integrations, or beta equals 4. So it's fairly straightforward in terms of how the filtering works. But in terms of generating pure noises for testing, this also allows you to generate a signal with a spectrum that's perfectly flat, so that when you fit the linearly squares fit slope, the slope is exactly 0.000, and you can fit the slope to whatever you want. If I wanted 0.587, I can actually get that exact slope if I wanted. So that if I was using this as a testing time series, I can use this as an input, and I know that any changes to this time series are a result of how my system is actually processing the input and changing the spectrum. So it gives me an easy way to map out the transfer function of how the system is actually changing any input signal. So that's basically the approach that I will use now to show how this works in audio. Now I will show a demonstration in audio. Okay, can you see that? All right, so right now I will load an audio signal. And this is going to serve as my emulation signal. So this is going to be the signal that I'm going to try to emulate. And I'm going to actually use a white noise with a beta value of 0 as the driver to this signal. So what this is actually doing is that I'm going to perform a short time Fourier transform on the audio signal, look at the spectrum of each frame, and then basically from the demonstration that I just showed in terms of where I was drawing the altitude exponent to create a filter, I'm actually going to take the differences between the driver signal and the emulation signal, and that will become my altitude exponent in terms of a filter to reshape the white noise signal into a new output. So if I just filter this audio signal, we have a new synthetic audio signal, and this is the short time Fourier spectrum waterfall plot of that signal, or the spectrogram. Up here is actually the filter for shaping this white noise into the so this is the filter for shaping the white noise into this spectrum. And if we play that, we'll play the synthetic version.
Mathematics, like music, is a language of its own with the power to transport us to alternative worlds and show us visions of other realities.
And the signal that this was emulated from sounds exactly the same because it has the same.
Mathematics, like music, is a language of its own with the power to transport us to alternative worlds and show us visions of other realities.
And the signal that was shaped, it's going to sound staticky.
And just one quick question. Can you talk about how when you go through that transformative process, what the synthetic output computationally is like? In other words, it seems to me that this is really useful for something that's out at the edge of the cloud, right, where you want to collect data in real time, but just transmit just the bare essentials. You don't have to actually transmit the whole signal. You're just essentially sending the filter values, right? Is that?
Well, you could. So you could. Let me just take one note of the clarinet because that would be easier to show. Okay, so that was a clarinet sound created entirely from the white noise. And when you look at the signal, so the original clarinet spectrum looks a lot like the synthetic one that's down here. You see the specific harmonics from each of the frequencies for that particular note. When you look at the spectrum of the filter from the white noise, you see that really, since this spectrum is mostly flat, you're just shaping, most of it is actually still flat in the part of the note that doesn't really matter very much. But in terms of the harmonics, that's where you're actually seeing that the filter for every frame is introducing some sort of peak value for those frequencies. One thing to note is when you look at the synthetic compared to the original, that there's really no loss in sound quality from the original signal to the synthetic signal, just created entirely from white noise.
Right, and again, coming back to my question, computationally, you collect a complex time series data out in the field, and you can either send it in a somewhat encrypted fashion or encoded fashion once you run it through the filter, right?
Correct.
Okay. And Martin, you had some questions or comments about this previously in relationship to embodying these algorithms on a GPU and what we'd like ultimately to have from partners in the, we're thinking initially that besides the audio realm in the biomedical, so ultrasound, EEG, other electrophysiology data. Do you have any questions or comments, Martin, about you know, what kind of value we can drive with potential partners using this filter technology?
That's a complex question.
Yeah.
I was thinking in terms of if this was used as a means of transmission, the actual filter matrix that you send there, certain parts of that filter matrix you actually you can decide not to send. So you basically have an adaptive system that looks and knows the type of signal that it wants to send and basically picks up on that one signal.
So excellent for feature detection. If you're looking for a specific physiological event that has a known signature, that could be ideal for that, right?
Yeah, that's correct. So basically you home in on the filter, so the filter is very specific to the type of data you're looking for.
Excellent. Okay. All right. Jeff, did you have anything else you want to present that gives an overview of the technology? I think what we're looking for from all of this is we want to get as many potential partners lined up as we can. We're applying to the state of Ohio for some developmental grant funding to embody the filter, to move it out of MATLAB, to get it into a GPU, and then develop a software and hardware kit with that so that we have something that's tangible and people can immediately perceive the value of this, right? This is our value proposition.
Right. Well, so one other thing I did want to mention was the ability to shape one audio signal into another audio signal. So you don't need to just use white noise to drive it. So for example, in this example, I have a clarinet signal. And that signal was created entirely from this other sound. So I don't know if you could hear, but one of them sounds a little bit out of tune, and then the other one is more in tune. So what this does is it actually shaped the signal here as the driver back into the original signal. So in terms of music synthesis or music processing, you can take one instrument and turn it into another instrument, one note, turn it into another note, or in terms of a noise canceling aspect from a different perspective. If you think about the human voice and speech, this would be an interesting way to do speech synthesis, because you could, there are 44 phonemes in the English language, or units of sound, which characterize the sound of our speech. And if you could break up each phoneme and have a catalog of phonemes for your voice, then instead of actually trying to filter noise out of a signal, if I was talking in a noisy environment, if I can identify the phoneme that I'm saying enough with a catalog of phonemes, I can then actually filter that phoneme with the noise in it back into the original sound for that phoneme, so I can resynthesize the speech without the noise and actually take that noise into the sound.
That's really impressive. Now, you had said something to me a couple of days ago. I want to make sure I understood correctly, and that is that if someone is running a brain scan of my brainwave activity in the auditory cortex, can you actually pick out signals that correspond to those individual 44 phonemes? And if so, could this then be used to essentially let a person speak just by thinking?
Yes, and there's been research. If you look up EEG and phonemes, you'll see that there has been research in this area where they've identified regions in the brain where they can map it to certain phonemes. And right now it's about, well, at least the papers that I saw from 2013, it was around 68% accuracy. So you might be able to increase the accuracy using the fractional scaling digital filters because you could isolate the EEG signal better. But then also, once you can map out, if you had a catalog of brain activity for each phoneme and then you had the catalog of phonemes for your voice, then what you could do is that when you find that activity for the phoneme in the brain, just either filter it into the voice or know that you'll have to just recreate that phoneme for voice, and then that would allow you to basically speak by thinking where you wouldn't have to have a microphone. So, I mean, think about for military applications where you could transmit a message without having to speak out loud.
Hey, that's great. Before we wrap up, can you give our viewers a sense of what kind of partner data we would like to get access to as we move this SDK and hardware together?
So we're looking for partners in a few different areas. One is audio, because there's a lot of potential in the audio space with these techniques. So either from a synthesizer point of view or a equalizer point of view, you have total control over your spectrum in terms of filtering out or amplifying specific frequencies. And then also in terms of speech, this offers a new way to do speech synthesis that does not need to have, in terms of like periodic impulses and white noise, you can actually synthesize speech entirely just from white noise or from any other signal. So that's in the audio space. In the medical space, there's a number of different applications. So from sensors, in terms of neuroscience, you could apply this to EEG data, MEG data, and basically any data that you have brainwave activity that can be filtered using these methods. So the methods are fairly straightforward. Also, in terms of medical data, medical imagery. So if I think about MRIs or other types of medical imagery, you can apply this not only in 1 dimensions but also 2 dimensions, and you can filter either an image as a static image, so that we're filtering the rows and columns, or you could filter that image through time in terms of isolating specific frequencies. So, for example, to extract the heart rate or respiration of somebody in a video, or to extract sound from a video based on the frequency changes of an object that's picking up the sound vibrations in the room.
Great. That's a super overview. So Jeff, you're at the Entrepreneur Center in downtown Dayton, Ohio. I'm making my office here at the Wright State Neuroscience Engineering Collaboration Building, also in Dayton. And Martin is in Newcastle in the UK.
That's correct. Northumberland.
All right. Okay, guys, I think that's a great overview, and we look forward to engaging with potential partners on this. I hope this gives them a great sense, and if not, we can certainly provide more technical details. All right?
All right, thank you.
Yep,
Thank you.
Thanks, everybody.